Hey everybody, sorry for needing to miss class tomorrow. I did want to uh, stay on track with everything, and so I wanted to finish our data diagnostics discussion where we were talking about normality. And just as a reminder, we had left off discussing the situation of skewness, where we discussed negative skew and positive skew and how to determine which direction it was. But really, the most important part was actually looking about um, where the mean was in a normal distribution, which is the important part of the normality assumption. So, those tests that use the mean as their key statistic, they have in their statistical tests and the mathematical foundations written in that that test will work most effectively when you have this nice pretty bell curve where the mean, the median, and the mode, your measures of central tendency, are all aligned in the center of the distribution. We also discussed the situation where you have a skewed distribution, in this case a positive one because you follow the tail, and remembering that the mean of the measures of central tendency is the most sensitive to extreme scores. So in this case of a positive skew, the mean gets pulled toward those low occurring high values, and what it does is it distorts where the actual mean should be, and that would be where the majority of the scores are falling. And so when you use a test that focuses on using the mean and you have a skewed distribution, you violated that normality assumption, and therefore the test that you use may lead you to some invalid results. And so last time we discussed two ways to kind of subjectively examine normality, and we used histograms and we used the QQ plots. We're going to start this lecture by talking about skewness values. And so as part of your uh, generation of descriptive statistics through the explore function, you will automatically get a skewness value of your distribution. And so we are going to actually put some numbers to this, and we're going to use a criterion that has been used in prior research. It's been published, it's used fairly frequently, and it's consistent with the criterion used in the book. But we're going to have an objective benchmark to which we can compare our skewness value after we have standardized it. So let's talk a little bit more about that. So the z-score criterion is going to come from Tabachnik and Fidel. It is not the only criterion that people have used. Personally, I think this is a very insensitive uh, criterion. However, I wanted to use one that was consistent with your book, as well as one that you would see in the literature. But what we're going to do is kind of break this down a little bit. So we're going to take the skewness value that we get with SPSS. We're going to divide it by a standard error value, which is right next to it, and you'll see in a second. And that's going to give us a z-score. Now, the sign of the z-score is going to tell us which direction the skew is. So if it's a negative value, it's a negatively skewed distribution. If it's a positive value, it's positively skewed. But if you have a value of 0 for skewness, which is very rare because there's always a slight skew, it's very rare that you have an exactly normal distribution. A 0 value of skew indicates no skewness and a normal distribution. Now, going back to what you hopefully recall from z-scores, a 0 value of normal, when you standardize a distribution, that 0 represents the mean, and when you compute a z-score, it gives you the value in standard deviation units away from that mean. So essentially, with the criterion we're going to use, we're going to set a value that says if we compute a z-score and it is higher than this value, then we're going to conclude that we have a significantly skewed distribution. So after we divide our skewness value by the standard error, we get our z-score. Again, that tells you the number of standard deviation units away from the mean, in this case 0 of the distribution, the skewness is. And the Tabachnik and Fidel value is plus or minus 3.29. So if you compute your skewness z, or your z-skew, and it is greater than 3.29 on either side of the distribution, whether it's positive or negative, if the number is larger than 3.29, you conclude that you have a significantly skewed distribution, and therefore it's a non-normal distribution. Any value less than 3.29 indicates to you that you have an approximately normal distribution based on these benchmarks. So let's briefly look at an example. Let me click over to SPSS. I've created a few numbers for us. So if we've got one single sample of scores, we want to know, is this distribution of scores normal or approximately normal? So if we do this, we're going to go to Analyze, Descriptive Statistics, Explore. We drop our dependent measure into the dependent list. We go to Plots, uncheck stem and leaf, check histogram, and don't forget to check normality plots with tests, because that's how you'll get your QQ plots, and it's also going to be how you get your 2 hypothesis tests of normality, which we're going to cover after kurtosis, in just a little bit. Once you've done that, you click OK. And then you wait. I know it's doing something. I can see it running down here on the right. There we go. So we had 20 scores, and if we scroll down, you again will see your histogram. That doesn't look very nice. Looks like it might be a positively skewed distribution. Here's your QQ plot. I would probably go with non-normal, because look how far this one is from that line. Again, that's consistent with a skew. This big 35 out here is likely that value there, driving there. But if we go up at the bottom of your descriptives box, you've got a skewness value right here of 1.504. And what we're going to do is we're going to take that 1.504 and we're going to divide it by the standard error, if you see this column here, and it's the value right next to it, the skewness value, 0.512. And what we're going to do is we're going to go and open a calculator real quick, and we're going to type in 1.504 divided by 0.512, and we actually get a z-skew value of 2.94. Okay, 2.94. Now if we go back to our PowerPoint briefly here, if you recall, we're comparing that to 3.29. So a skewness value standardized has to be 3.29 standard deviations away, either above or below the 0, in order for us to conclude that we have a non-normal distribution. Our value, 2.94, is less than 3.29, therefore we conclude that it is an approximately normal distribution. In other words, we do not have a significant skew because it was not beyond 3.29. Now, something to consider, as I've told you earlier, personally I feel that these are very large values. I mean, we have something that's almost 3 standard deviations away from the mean. And that's something that you'll be able to take into consideration if you wish. I'm fine if you stick straight to the benchmarks, but again, part of this class is using information, using data you have to make some educated decisions about whether you meet some assumption checks, which in turn will drive you to maybe select different statistical tests that you feel might be better. But in this case, sticking strictly to the criterion value of 3.29, 2.94 is not greater than that. Therefore, we conclude that we do not have a significantly skewed distribution, and therefore it is a normal or approximately normal distribution based on this particular screening. So that's how you do the skewness screening. Let's talk a little bit about kurtosis. And what you'll find about kurtosis, it's a different look on a distribution, but you're going to use the same procedure with the same Tabachnik and Fidel criterion to make a decision on whether you have uh, some violations of what a normal distribution would look like in terms of kurtosis. So kurtosis really overall deals with the relative concentrations of scores as they occur across a distribution. So if we look at this diagram, I'll start by pointing out what's called mesokurtic. So that's the black, nice little curve in the middle. If you have a mesokurtic distribution, you have a normal distribution. In other words, in terms of concentrations of scores as they fall through the distribution, they fall in such a way that they gradually, as they move out to the tail, you have a decrease in the amount of scores that fall in those areas as you move toward the tail, such that you get that kind of nice breakdown of a normal distribution, right? So the 68% fall within one standard deviation of the mean. 95% fall within two standard deviations, 99 within three standard deviations. Now, in this particular case, that's your normal distribution. If you have more falling in the center, that tends to drive the distribution to be pointier in the middle. It's going to be called a leptokurtic distribution. So you have more falling in the middle that drives it up to a point and fewer scores falling out as you move to the tails. So that's a leptokurtic. If you have a flatter distribution, meaning that you've got uh, a more relatively spread amount of scores as it moves across the distribution, leading it to look like a flat distribution, you have a platykurtic distribution. So just remember plat, flat. Okay? But all of the kurtosis is about the relative concentrations of scores as you move through a distribution. The pointier is lepto, the flat is platy, mesokurtic is approximately normal distribution. Now, when we screen for kurtosis, you're going to get a kurtosis value. Okay? Kurtosis uses different ways to look at a distribution to identify where scores are falling through that distribution to get a shape, essentially. But again, you're going to get a one kurtosis value. I don't require you to remember and learn how to compute kurtosis, but we're going to use the same process that we did with skewness, where we get a kurtosis value as we run our descriptives. The sign of that value, if it's positive, that indicates that you have a distribution that's a little leptokurtic. If you have a negative in front of your kurtosis value, that indicates that you have a somewhat flat distribution. If you have an exactly zero value for your kurtosis, that is a mesokurtic or normal distribution. Okay? Again, that's very unlikely. It's very rare that you get a zero value here, and it's exactly telling you it's a normal distribution. There's always a little flux, and so you will have something maybe a little on the positive side or a little on the negative side. And what we're doing here is we're going to divide that kurtosis value by the standard error again, and we're going to get a z kurtosis value. And then we use that same criterion, 3.29, to determine if that value is far enough on either the leptokurtic or the platykurtic side for us to conclude that we have a significant deviation away from a mesokurtic or a normal distribution. So if we compute it and it's not greater than 3.29, we conclude based on Z kurtosis that we have a normal distribution. If it's beyond the 3.29, we conclude that it is a non-normal distribution. So if we go back and we look at our example, I'll just pull up the output. So in our descriptives box here, you can see you get a kurtosis value. It's positive, which should indicate that it's leptokurtic. Okay? So 3.256, and right next to it, again, just like the skewness, you have a standard error value. And what we're going to do is we're going to take our 3.256 and we're going to divide it by our standard error 0.992, and we're going to get, wow, that's close, we're going to get a Z kurtosis of 3.28. Okay, 3.28. And if we go back to our criterion of 3.29, it's very close, but it's not beyond the benchmark criterion. So if it's not beyond it, you should conclude it's approximately normal if you stick hard and fast to that 3.29. So 3.28 is just under 3.29, therefore you can conclude it's approximately normal based on kurtosis. Now, given that it's so close, again, I will tell you, you can factor that into your decision making, right? So you've looked at the histogram, you've looked at the QQ plots. Neither one looked very good, if I recall. Then you get here and you've got some fairly high Z skewness and Z kurtosis values, okay, that may, in your mind, even though they're not at that benchmark, they may indicate to you that there's a lot going on here, and it may not be an approximately normal distribution once I start to weigh all of the evidence. Again, it's okay to stick to those benchmarks. I'm perfectly fine with that. But it's also okay to think more critically about it to see if you come to a different decision, just make sure you tell me that decision, okay? And why, even though you didn't meet the benchmark or beat the benchmark, why you still think it's a little bit non-normal, okay? So that's how you do skewness and kurtosis screening. And the next part actually brings us back to our hypothesis testing model. And when you run descriptive statistics using the explore function, you will automatically get two hypothesis tests for normality. One of them is the Shapiro-Wilk, and the other is the Kolmogorov-Smirnov. Now, these are different in terms of what they should be consulted for. Shapiro-Wilk is generally used when you have a smaller sample size. It's got some mathematics involved that help adjust some values for having smaller sample sizes. And the Smirnov test is usually for larger sample sizes. Now, given what we've talked about, there are lots of different guidelines for using these. I tend to like the 30 cutoff because that's the theoretical number for, if you remember back to central limit theorem, law of large numbers, etc., 30 observations is that theoretical number that if your population of whatever your dependent measure is actually shows a normal distribution, then at about 30 scores or 30 observations, you should approximate that. And so in this class, what we'll use is for Shapiro-Wilk, if you have a sample size that is lower than 30, then I want you to consult the Shapiro-Wilk. If you have a sample size that is 30 or more, I want you to consult the Kolmogorov-Smirnov. Now, like I said, these are both hypothesis tests. And I want you to remember that the logic of hypothesis testing does not change across statistical tests. It will remain the same. It will remain the same for every statistical test that I teach you from here on out. For this particular set of tests, both normality tests have the same null hypothesis. They both enter into a situation with the null hypothesis that your distribution is normal. In other words, your distribution is not different than a normal distribution. And then you go through, you're going to run this, you'll get a p-value. If your p is greater than or equal to your alpha, 0.05, you're going to fail to reject that null hypothesis, and you're going to conclude that you have a normal distribution. If your p-value is less than your alpha, you're going to reject the null and conclude that you have a non-normal distribution. Now, these particular tests are actually quite sensitive to deviations from normal distributions. And the reasoning being is it's taking a closer look at multiple parts of that distribution and how it relates to what a normal distribution would look like. So it's going to be more likely to catch deviations from a normal distribution. And to me, relative to the skewness and kurtosis screening, it has a lower threshold for detecting deviations from normal. So if we go back to our example, we'll keep using the same one. Underneath your descriptives box, you should see a little box that says tests of normality. Okay? And like I said, regardless of whether you want one or not, you're going to get them both. And you have to make the decision about which one to consult based on how many observations you have in the sample. Now, when you look at these normality tests, they don't do the n-1 degrees of freedom. They use all the observations to detect any deviations from normal. So when you see under DF and you see 20, that's how many observations you have. If you don't know this, you can go up to how many valid cases you had, and it says 20 as well. So knowing that we have 20, we know that Shapiro-Wilk is formatted for situations where you have less than 30 observations. So we are going to consult the Shapiro-Wilk test and ignore the Smirnoff test. Now, the statistic for Shapiro-Wilk, that's what's calculated. It's actually a W statistic. But what's important for us is the p-value. For this particular test, we have a p-value of 0.022, which falls below our alpha of 0.05. Since that p is less than alpha, I'm going to reject the null. And in this case, if I reject the null, what I'm saying is that I have a non-normal distribution. So now, one thing to point out, if you had selected the Smirnoff test, okay, you would have come to a different conclusion. Okay? But the Smirnoff is not the best test to consult here because it's not above 30. Okay, so it doesn't have 30 or more. So the Shapiro-Wilk tells us we have a non-normal distribution. So if after we weigh all of our evidence, so if we recall, the histogram appeared to be non-normal, the QQ plot appeared to be non-normal, the skewness and kurtosis, if you go strictly by the 3.29 criterion, neither one, after we converted to a z-score, was beyond 3.29. Therefore, we could say that they're approximately normal. So, histogram, non-normal. QQ plot, non-normal. Z-skew, normal. Z-kurtosis, normal. And then the last, the Shapiro-Wilk, the more sensitive of the measures, we decided, given our p-value of 0.022, to reject the null and conclude that we had a non-normal distribution. Now, one way to weigh all of that evidence is I've got three non-normals, one of which is the Shapiro-Wilk, and it's the most sensitive. Therefore, I conclude overall that this distribution is non-normal. If you're tied to the z-skew and z-kurtosis, those led you to a normal conclusion. Again, you'd have to explain that in your decision making. However, you could also add in those of you who are leaning non-normal on this one, those two z-skew and z-kurtosis, even though we did not meet or surpass, the 3.29, they were still very large numbers, one of which was only, it was 3.28. And so it was right there. So that actually, despite not meeting the criterion, could figure into your decision making. And you could argue that this is overall, for the most part, a non-normal distribution. Personally, I would have concluded non-normal, especially given the Shapiro-Wilk and what the histogram looked like. But I would also think about those large z-skew and especially z-kurtosis values. Now, what I want you to do, so for tomorrow's class, you are going to do the following as part of the activity. You don't have to do this during our class time, but you will email me something by the end of the day. So here's a basic activity. What you're going to do is you're going to go into SPSS and you're going to create a single sample of scores on your own. Doesn't matter how many you have, doesn't matter the range of the scores. Okay, just create a single sample of scores. And then you're going to use SPSS to do what we just did. You're going to generate your descriptive statistics using Analyze Descriptive Statistics Explorer, making sure that you check the histogram and you check the normality plots with tests. And then you're going to look at all of these pieces. You're going to look at the histogram, make a decision. Look at the QQ plot, make a decision. Compute your z-skew value and compare it to 3.29, make a decision. Do the same thing with your kurtosis, convert it to a z-kurtosis value, compare it to 3.29, and make a decision. And then last, depending on how big your sample is, you're going to either consult the Smirnoff test or the Shapiro-Wilk and use that hypothesis test to make a decision about whether it's normal or not. And then you will weigh the evidence. Okay? And essentially what I want you to do is in a Microsoft Word document, type up your decisions about normality for each diagnostic test, histogram, QQ, z-skew, z-kurtosis, Shapiro-Wilk, or the Smirnoff, and your final conclusion after weighing all of those individual decisions. Please email this document and your SPSS data set to me by the end of the day tomorrow, 11:59 p.m. Eastern Standard Time. And that way I can take a look and offer feedback before you take the quiz over the weekend. The other thing that I'd like you to do, I'm not going to require you to send me or write me a response for the supplementary reading, but I do want to make sure that you have it read and be ready to discuss it when we meet on Tuesday of next week. So this is the supplementary reading that goes along with Chapter 6. So you don't have to do anything but have it read by our next class on Tuesday. Now, in terms of the quiz, please send me this activity so that I can look at it and give you some feedback. Also, be sure that you read the description of the quiz, review the information, so it's only going to be over data diagnostics, especially focus on what we've talked about in class and the normality assumption, as well as being able to make a decision given the descriptive statistics that you're practicing for the activity. Now, given that Monday is Labor Day, I will not make the quiz due Monday at 9:30. So this quiz will open 9:30 Friday morning and it will close 9:30 on Tuesday morning. So please don't worry that you have to have it done on Labor Day. You do not. It's due Tuesday morning at 9:30. If you have any questions, feel free to email me. But I'm going to be back in the office no later than 2 o'clock on Friday. So if you need to see me that afternoon, I will be there. Otherwise, I hope you enjoy your Thursday. And again, I'm sorry for missing. I know many of you are distraught that we are missing class, but don't worry, I'll bring some extra music on Tuesday and we'll get some stuff done.